Okay, good morning, everyone. So I hope everyone has a good break. Well, technically today is still a holiday, but um, well, this is the holiday that we are allowed to have class. So let's have class, right? Because otherwise, there's really nothing to do. Okay, last time we talked about three equations mostly. Well, I listed four. But the first two are the same equations, this one. So the first two equations describe property of gas, right? So this is what is called the ideal gas law, okay? So main functionality of these two equations are to relate three important properties of gas: the pressure, P, volume, and temperature here. Okay, so from this, then you can essentially calculate how gas change its property when you compress it, when you heat it up, or when you like make the container larger, so you change the volume. Okay, so we're gonna be using quite a lot of these two equations for like a lot of applications towards the end of this lecture, and maybe also at the beginning of the next one. And then the other two equations that we talk about is these two, Q equal to mc delta T. So this one is the heat required to change temperature for any substance. Okay, so you know already from your daily experience that if you want to increase the temperature of anything, then you need to put in heat. If you want to reduce the temperature, then you need to take away heat from that object. And everything is fine until you hit what is called the phase transition. That's when you go from solid to liquid, liquid back to solid, or liquid to gas, something like that. Right. So every time you have phase transition, it takes extra energy to go across different phases, and the amount of heat that you need to go across different phases is given by this equation. Okay, so this is heat. Okay, same thing, heat required to change phase. Okay, different phases to require energy to go across. All right, so we're going to talk about one final thing about phase, which is the phase diagram, in a few minutes. But before that, let's review a little bit of what we learned last time by doing these two very simple equations, problems. Okay, so the first one is rather easy. You actually don't need to do any calculation, right? So what I'm asking here is that we have 200 grams of water. So that's the mass of water, and then it's at 0 degrees Celsius. Okay, so water can have 0 degrees Celsius, right? But if you want to go below that, then you need to become ice first. But this is fine. And then we mix this 200 grams of water with another 200 grams of water, but now it's 100 degrees Celsius. Okay, so what is the final temperature? What is the final T? Well, this one, you don't need to do any calculation. It's actually, you can calculate it like quickly in your head, because like you have 0 degrees, you have 100 degrees, and they have the same mass, right? So in the end, it should be halfway once you mix them. Okay, so the answer for the first question is simply T final equal to 50 degrees Celsius. Okay, this is because we have the equal amount of water at two different temperatures. If you don't have the same amount, then you need to do a little bit more. Like you need to think about how much heat is lost by this part, how much heat acquired by this part, how much heat lost by this part, and then the final temperature has to be the same. Right? So that's the way to calculate. Even more interesting is when the problem involves phase change. So problem number 2 is almost the same as number 1, except that I start with 0 degrees of ice instead of water. Okay, so one thing that I need to kind of remind everyone is that ice can have temperature less than 0. Okay, for some reason, sometimes you might think that ice always has to be 0 degrees Celsius. That's not true. Okay, so ice can be 0 degrees Celsius, it can be -5, -10, -100, whatever low temperature you want to have ice. Okay, so but in this case, ice at 0 degrees Celsius, and it's the same amount, which is 200 grams, and it's mixed with 200 grams of water, which is at 100 degrees Celsius. Okay, so this one is more complicated. So how to actually solve this one? So every time you have something like this, I suggest that you kind of draw a diagram on what's going on, right? So what I will draw is I will draw the 2 parts of this problem, which is ice, the ice part. Okay, so that's ice. And 0 degrees Celsius, 200 grams of ice. And then the other part I will draw is the hot water part. Okay, that's the 2 things that we're gonna mix together. So we have hot water. Hot water is at 100 degrees Celsius and also 200 grams. Okay, so we assume that well, when ice melt, then water is a little bit colder, but that's not what you have to assume. That's probably something that's gonna happen for sure, right? But we have to assume that when you mix everything up, in the end, there's no ice left over, right? That's our assumption. Whether that's true or not, the calculation will show, okay? But let's assume that's the case. What that means is that the first step that I'm gonna draw here is for ice become water, right? So all the ice melt and becomes water. So during this process, remember that during the phase change, you don't change the temperature. So from ice to water, the temperature is the same, 0 degrees Celsius and 200 grams. Okay, but during this phase change, you need to put in some energy, right? So where does that energy come from? It has to come from energy of the hot water, right? So I'm gonna draw using red arrow here, the flow of heat, which is this way, right? So hot water become colder, ice melt, so energy gonna flow this way, okay? Heat gonna flow this way. But when you lose energy on the right hand side, the temperature of hot water must go down, right? Because otherwise you don't conserve energy. So during the same step here, on the right hand side, water which start at 100 degrees Celsius becomes something colder, okay? So we don't know what's the temperature here, we can calculate it, right? But this is the second step that we need to draw, all right? So you can view the vertical progression like this as like timeline, right? So as time passes, then you go down this diagram, okay? And the last step is for the left hand side, water to reach some final temperature, let's say TF. and then the mass is the same. So actually, I don't need to keep writing the mass, right? So let's not do that because we don't need to waste our space doing so. And then the right-hand side, T1, I don't know, maybe that's 80 degrees. We need to calculate it later. But eventually, it will also cool down even further. And where does it end? Well, things will stop exchanging energy when they reach the same temperature. So you have TF here and TF here, which is the same temperature. And that's the last step, okay? So our task is to find what is TF here. And during this time, again, heat must flow this way. So actually I can write Q1, I can write Q2 here just to indicate clearly the two steps. All right, so let's calculate the first step here. So we need to melt 200 grams of ice. How much heat do we need for that? So what equation do we use? Well, this involves phase change, right? So the first part, like actually I'm gonna erase that, right, 200 grams here. So the first part is to calculate heat required to melt ice. So Q1, which is for melting ice, that's simply equal to one simple formula, right, that we have earlier. So Q1 equal to M times L, right? So M is 200 grams. That's 0.2 kilograms. And what is L? Well, L is latent heat for fusion, right? If you look at the table that we had from the last lecture, we need to use fusion because the other one is vaporization. That's for boiling or condensation. That's not what we want. So for fusion, you have about 3.33 times 10 to the 5 joules per kilogram. So when you calculate this, then you get about 6.66 times 10 to the 4 joules. So that's how much heat you need to melt this chunk of ice, which is 200 grams. Okay, so that's the first step. So in this step, we can kind of fill in the diagram here. So I can write Q1 is 6.66 times 10 to the 4. Okay, so while doing the calculation, you can also check if I do it correctly. If not, you can let me know. So Q1 has to come from hot water. So hot water needs to lose 6.66 times 10 to the 4 joules, right? So in the end, we need to calculate, okay, after losing this much energy, what's the final temperature of the hot water, okay? So we need to calculate T1. So hot water lose energy, so it's gonna be negative Q for hot water, right? So this is where the sign will become a little bit difficult if you're not careful, right? So just be aware of the sign in this way. So for hot water, we have, so hot water, we have Q1 equal to, let's put the prime here because it's to indicate that it's going to flow away from hot water, equal to mc delta T. Okay, so, and Q1 we already calculated, it's going to be minus 6.66 times 10 to the 4. Again, it's minus sign because from the point of view of hot water, it's losing energy. All right, so heat flow away. And M is 0.2. C is the heat, specific heat of water. And that's going to be 4,000, roughly 4,200 joules per kilogram per degree Celsius. Okay, so that's C. And then what is delta T? Delta T is the final temperature minus the initial temperature. So that's going to be T1 minus 100. Okay, so sorry for small font, but I want to fit everything in a single line here. All right, so now if I calculate this, so 6.66 times 10 to the 4 divided by 0.2 divided by 42000. So I got left hand side to be minus 79.3 equal to T1 minus 100. Okay, so just a simple math here. So that means T1 T1 is equal to 20.7 degrees Celsius. Right, so from solving this equation, you can get what T1 is. Okay, which is good. The thing that we are afraid of is that T1, by solving this equation, going to be less than 0. If that's the case, then we know that even if all the hot water lose all the energy to reach 0 degrees Celsius, it's not enough to melt all the ice. Okay, so that's going to show in this step. And that can happen. For example, I can simply increase the amount of ice we have here from 200 to 400. If you repeat this calculation, then you're going to get T1 to be negative, which cannot be the case. Okay, so if that happens, then you know that it's not enough energy to melt all the ice. And that's going to be totally different problem. But in our case, we have enough hot water to melt all the ice. So T1 is 20.7 degrees Celsius. Okay, so now we can move on to the next step, right, which is what is the final temperature after both of them now becomes water. Okay, so this is water at 0 degrees, this is water at 20 degrees, 20.7 degrees Celsius, right? So now the problem is kind of the repeat of the first problem, all right? So, okay, so quick question here. So why is it T1 minus 100? So what is delta T? Delta T is final temperature minus initial temperature, right? So the final temperature is T1. The initial temperature is 100, right? So that's why it's T1 minus 100. Instead of 100 minus T1. That's kind of the other way around, which is wrong. Okay, so that's why the minus sign here is very important, because you go to lower temperature, you have to lose heat. So Q must be negative in this way. So if you don't do this, you say it's 100 minus T1, then the final temperature will be something really strange. Okay, so you have to be careful here. All right, is that okay? All right, so let's proceed to the next step. The next step is to mix water, okay? And this one is 200 and 200 grams, so you can just do the average and then you can get the answer right away. But I'm gonna show you kind of like the proper way of doing, but in the end you're gonna get the same answer anyway. All right, so we're gonna calculate what is TF, right? So from the point of view of the left-hand side, it gain energy, right? So from the left-hand side, we're gonna have the equation that looks like this. So M equal to MC delta T, right? So delta T is TF minus 0 degree Celsius for the left-hand side. Okay, so that's going to be equal to Q2. Okay, and we know that Q2 must be positive flowing into this part, the left-hand side, because it's getting hotter, right? So just to make everything absolutely clear, I'm going to put an absolute sign here to make sure that it's positive so that we are not confused about the sign of Q. Okay, so that's for the left glass of water. Now for the right one, it's getting colder, right? TF is less than 20.7 for sure, right? So you're going to have on the right hand side MC. Now delta T is going to be TF minus 20.7 degrees Celsius. And this one will be related Q2, that's for sure. But it's getting colder, so that means it has to lose energy, right? Losing energy means Q is negative. So I can write negative and then this absolute sign here just to make sure that I'm not confused about the sign of Q2, right? So I cannot just write minus Q2 like this because like Q2 here from the point of view of the right hand side and Q2 from the point of view of the left hand side, they are actually opposite sign, right? So by writing it like this with the absolute sign, then I can be absolutely sure that I'm not messing up with the sign of the heat transfer. Okay, so think about this carefully, right? Why I'm doing this. And if you don't do this, then you're gonna mess up the calculation. So we can now equate the two equations together because here we have absolute value of Q. This we have absolute value of Q. So we can make the two equations equal to each other. So what I'm gonna get in the end is MC. Let me change the color. MC TF minus 0 on the left hand side, that's Q2, equal to also Q2 here, right? Absolute value of Q2. So it has to be minus MC TF minus 20.7 degrees. Okay, so the minus sign here comes from the fact that this is minus absolute value of Q2, which is the left hand side. Okay, so the minus sign here is very, very important. Otherwise, you're gonna have the wrong answer. And they have the same mass, so mass cancel out. Same water, so C cancel out because specific heat for water on both sides, right? Give you the same number, so you can just cancel out. So in the end, what you have is TF equal to minus TF plus 20.7. And this one leads to TF 2TF equal to 20.7. So TF is simply 20.7 divided by 2. So that's going to be 10.4, roughly 10.35 degrees Celsius. Okay, so again, the right-hand side is negative because the right-hand side is losing energy, right? So it's negative Q, negative absolute value of Q2, right? So when you equate the two equations, you need to equate left-hand side and right-hand side, which is the same, right? So left-hand side is Q2, but right-hand side has to be also Q2, but this thing is minus Q2, so that's why I put the minus sign here, all right, to make the two sides exactly equal, and that's a valid equation. Okay, so I hope that clear things up. All right, so you can see that just by changing one thing in the problem, the calculation becomes, well, quite a lot more complicated. And that's just the way it is for this kind of problem, right? So you have to be careful to check every step that, okay, if the phase change happening, if water is enough to melt ice, if not, then what's gonna happen? All right, so this one required quite a lot of thinking when solving any more complicated version of this problem. But you get the idea on like how to solve this kind of problem. Okay, so this is kind of what we talked about last time and then apply to these two problems. So what do we gonna talk about today then? Well, we're gonna talk a little bit about the phase diagram and then heat conduction. And then we're gonna start talking about another big topic, which is thermodynamical processes. So we're gonna start with the PV diagram. And then if we have time, then we're gonna talk about thermodynamics, like the first law of thermodynamics, and then calculate how we can use gas to build an engine, which is called a heat engine, which is essentially what's happening in every internal combustion car, which is slowly being replaced by electric car, right? So maybe what we learn today will become a little bit less relevant in a few years in the future. Okay, but anyway, that's our plan for today. All right, so let's talk about the phase diagram. So the phase diagram is kind of like a map that shows you how for a certain type of material can change phase, and then we're gonna see where that happened, when that happened, in terms of pressure or temperature. Okay, so let's look at this phase diagram. So the first one we see here, that's for water. Okay, so we know already that water has three phases, which is solid, that's essentially, let me zoom in a little bit, that's essentially ice. And then liquid, that's normal water. And then gas, which is called vapor for water. Okay, so this is what we call a simplified diagram, because in reality there's a lot of details in water. Believe it or not, water is actually one of the most difficult matter to understand from the point of view of physics, because the way molecule is formed, like a lot of you probably know already that water, the chemical formula for water is H2O, right? So 2 hydrogen and 1 oxygen. And oxygen at the center is joined by hydrogen like this. And the fact that it's not oriented in a straight line makes the structure of water, ice, all that stuff, well, very interesting and also very difficult to calculate. All right, so that's kind of what we are dealing with here. But this phase diagram is a very simplified version of the actual one. So you can Google the actual phase diagram for water, and then you see that it's very, very complicated. And even ice, there are like more than one type of ice, right? There are like ice 1, ice 2. That sometimes sounds like, like different kind of ice spell in RPG game or something like that. But it's just, like different crystal structure of water that can happen depending on water and depending on temperature and pressure. Okay, but anyway, let's say what we have here. The vertical axis we have here is pressure. Okay, and horizontal axis is T, which is temperature, right? But remember, from ideal gas law, we have PV equal to nRT, right? So actually we need 3 parameters to describe like why is this plot in a 2-dimensional graph. Well, because if you know 2 of them, you can calculate the third one, right? So you know P, you know T, then you can calculate V, which is the volume. Normally, volume is kind of arbitrary, because like you can have a lot of water in a large bottle of water, and you can have, like small amount of water, right? So that's why V is not really on the graph, because that's the parameter that kind of not, it's something that can be easily changed, right, by just changing the container size. But pressure and temperature, that's mostly determined from the environment. So that's why it's plotted with these two parameters. Okay, and the horizontal axis is in degrees Celsius, so that's something we are used to. But the vertical axis pressure is actually in ATM, right? So what is ATM? Is this the place where you get cash from? Well, not really the case, right? ATM is actually a unit of pressure, which is which stands for atmosphere, right? So it's the pressure of like normal atmosphere. So what we are experiencing right now is roughly about 1 atm, right? So 1 atm is the standard pressure for like regular elevation, not too high and not too low, right? So that's about 10 to the 5 Pascal. So it's pretty high. So you can see that on this diagram, right, 1 atm is basically the normal condition that you're going to experience. So that's one. So the line horizontally going through this graph, like here, everywhere on this line, that's 1 atm, right? So at 1 atm, you can have different temperature. And depending on the temperature, you can have different phase of water, right? So if we stay at 1 atm, if you are here, right, that means you are lower than 0 degrees Celsius. So obviously you're going to have ice. So that's why it's in this region, which is solid region. So that's ice. When you go across this line, you go from solid to liquid. So if you are above 0 degrees Celsius at 1 atm, you are in this region, so you're going to have water, right? So going from solid to liquid for water is ice melting, right? So going across that line, that's the phase transition. And then when you increase the temperature even further, you go from liquid to gas, that's boiling, and that happens at 100 degrees Celsius. Okay, so that's how we look at the phase diagram. And the thing is that when we say water boils at 100 degrees Celsius, that's not always the case. Because if you want to say so, you have to tell what pressure are we talking about, right? So if some of you might have like hiked up to the mountain before and then you try to boil water, and then you realize that water gonna boil at not at 100 degrees Celsius, but a little bit lower. So what's happening there? It's because when you are high up on the mountain, the pressure drops. So you're no longer at 1 atm. So the pressure is going to be something like, I don't know, a little bit less than 1. So maybe it's going to be this line. Okay. So let's say this is the pressure P on the mountain. Right. So it's going to be lower. So you can see that when you lower the temperature, when you lower the pressure to go across from liquid to gas, you actually don't need to go to 100 degrees Celsius. It's going to happen a little bit lower. Okay, so that's why it boils at lower than 100 degrees Celsius. So when you cook anything there up on the mountain, it's going to taste a little bit different compared to the normal condition because it's just not as hot. Coffee will taste worse. Tea will taste worse. Okay, so that's kind of the thing. And this is also the reason of pressure cooker, like why pressure cooker reduce a lot of cooking time. Because pressure cooker can build up pressure in the pot, right? So it's gonna have more pressure than 1 atm. So pressure cooker might have pressure at this line here, I don't know. And then you can see the boiling point actually increased from 100. So maybe it's 110, 120, right? So then that means you can cook stuff at higher temperature, because remember that until all the water boils, you're gonna stuck at boiling point. Right? That's what happened at the phase transition, is that the temperature will not change until everything changed to the new phase. Then temperature can increase again. But normally when you cook something like stew or soup, right, you're not getting rid of all the water, right? So the temperature is stuck at boiling point. So the pressure cooker is a direct way of increasing the boiling point of water by building up pressure. Okay, so that's kind of the thing about this water. Another thing which is important on this diagram is this particular point. So that's called a triple point. A triple point is the point where three phases can coexist. We don't see this because to see this, you have to go to a very low pressure. This 0.006 atm, that's too low for us to survive. So this is gonna happen in the laboratory when you make a vacuum container, and then you can observe this triple point. But you can Google in YouTube, I think, and then see how it looks like. Just say a triple point of water, and you're gonna see that really you're gonna have ice, you're gonna have water, and then you're gonna have vapor. So it's a very bizarre thing to take a look, because you have ice, you have water, and all of those things is boiling at the same time, right? So that's a very strange thing to happen, but it can happen. So that's what triple point means. Okay, so different kind of material will have different phase diagram. For this one, we have carbon dioxide. So we talked about this last time in the form of dry ice. So dry ice, the one that you get from ordering ice cream, is a solid form of carbon dioxide. Okay, and if you observe carefully, you're gonna see that dry ice will not melt, but it's gonna evaporate right away. Right? So if you have dry ice, then it will not melt like water. It will just evaporate, becomes carbon dioxide. Right? So you can get some, and then you can see if this is the case or not. And why is that? Because if you look at the phase diagram of dry ice, you can see that at 1 atm, the phase diagram looks like this. So at 1 atm, you're on this line here, right? So when you go across from solid, you don't encounter any solid phase, any liquid phase here, right? So you go straight from solid to gas, and that's why you don't ever see liquid dry ice or liquid carbon dioxide under normal condition, right? So if you really want to see liquid carbon dioxide, you have to increase the pressure to be a lot higher than normal atmospheric pressure. And that's what happened in a tank. Like you probably have seen maybe in a movie that you have like high pressure tank that contain various kind of gas. So in that tank, gas becomes liquid. So it's stored in the liquid form. And then when you use it, you release the pressure, so it becomes gas. And that can happen because in the tank, the pressure is a lot higher. So maybe here. So you can have liquid in that case, right? So that's different pressure gives you different behavior of the material. All right, so different material will have different phase diagram, and you have to look for different, really different unique phase diagram for each material. There's no kind of universal phase diagram that applies for every material, and that makes it actually quite interesting if you are really into this kind of stuff. Okay. So that's for the phase diagram. Any question you want to ask during this time? Well, just leave me the message if you have anything to ask. Okay, but the next thing I want to talk about is heat conduction. So if we go back to this thing briefly, right? So you can see that we have two parts that is exchanging heat, like ice and water. And they exchange heat because you directly mix them, right? And sometimes you don't directly mix them. Sometimes you kind of, let's say you put water in the pot and then you heat up the pot, right? So you don't mix fire with water because that just doesn't work, right? So you have to have some material which, conduct heat, like heat can flow through that kind of material. So we are not gonna talk too much about, like different kind of heat transfer, but we'll talk about one specific thing, which is heat conduction, because that's probably more important in a sense, because it's more related to the thing that you are used to in daily life. Okay. So in general, we're going to have what we call heat transfer. And one form of heat transfer is called heat conduction. So heat conduction is something that can be understood quite easily. If you imagine that you have, let's say, a block of aluminum or copper, right? And then let's say you are holding this block with two hands on one side, and then you heat up the other side of this block of aluminum, right? So this is fire, okay? And well, you probably know what's gonna happen eventually is that the left-hand side will get hot, right? And then eventually you're gonna feel yourself on the right-hand side, which is far away from the heat source, gonna get gradually hotter and hotter also. Right. So what happened here is that this side absorbs some heat onto the block, and then it transfers heat along this bar, right? So that the other end will eventually become equally hot, right? So this kind of heat transfer is called heat conduction. It's called heat conduction because there's no movement of the material itself that creates this heat transfer. Right, so the block is staying there still. The block is not moving, but somehow it can conduct heat. This is different from the case where replacing with the block of aluminum or copper with, like a fan. Let's say you have like a fan, right? And then you have like heat source here. So you have fire, and then you are standing here, right? So eventually you're gonna feel some kind of, like hot air hitting you, and you will feel warmer. So that's also heat transfer in this case, right? But in this case, the thing that transfer heat is air molecules really moving along with the energy it's carrying, right? So in this case, the thing which is responsible for, like heat carrying is air, which is moving together with the energy, which is different from what we have up here. Okay, so that's the difference. Whether the conductor itself moves with the with heat or not. So this is called heat conduction. The one below is called heat convection. Okay, so it's like, you know, air conditioner where you produce cold air and then you blow cold air to you, right? So that you feel not as hot, right? Which is totally different from heat conduction. So heat conduction is when you cook something and then the whole pan becomes, you know, like hot, right? So that's the difference. Okay, heat convection is pretty hard to calculate because it involves the flow of water, the flow of, you know, air, and that's very, very complicated. So that's why normally we don't really talk about it. It's just very hard to say anything quantitatively. So we're gonna talk about conduction pretty exclusively here. So what about conduction? Well, imagine that you have, you know, again, a block of something, material which can conduct heat. Okay, so let's just put in some parameter, right? So you can think of this as, you know, like the wall of your room or something, and then outside is really hot, right? Especially now, you have like hot outside temperature. Let's say T outside, let's say 40 degrees Celsius, okay? And then you are here, right? What you're doing, well, you are maybe looking at the lecture, right? So you're looking at the laptop here, right? And it's all cold inside, right? So let's say 20 degrees Celsius here, right? It's 20 degrees Celsius because you have like the air conditioner inside that is keeping the temperature cold. What if you turn off the AC? Eventually, inside temperature will be the same as outside. Right? So you become, you know, hot again, and you need to turn on the AC one more time. Okay, so that means when you turn off the air conditioner, right, there's heat transfer from outside to inside. Right, so that's why the room is getting hotter and hotter. So there's heat transfer from outside to inside here, Q. And essentially we want to describe how Q depends on the property of the wall. Right? So the basic kind of parameter here we're going to write down is the length of the wall, or the thickness, let's say is to be L, and the area of the wall, let's say, is A. Okay, so let's say we have these two things, and the other thing that gonna influence like the value of Q is the difference of the temperature between outside and inside, right? So all of these together, we can write something like this. So we can write P, which is the power. Okay, power is defined to be the heat flow Q divided by time. Okay, so the longer you wait, of course, more energy gonna flow. So it probably makes sense to define the power instead of heat directly. So Q over T, okay, Q over time is power. Power has the unit of watts. So watt is joules per second. Okay, and it's gonna depend on a couple of things. It's gonna depend on the area. The larger the area, the more heat transfer you have. The difference in the temperature, okay, so T outside minus T inside. So that's delta T. And then divide by the thickness of your wall. Okay, so now different material gonna have different ability to transfer heat, right? So in order to capture that, we put in a parameter here which is called K. So K is what we call thermal conductivity. And this is just like specific heat, is parameter that depends on material. Okay, so different kind of material, how do you account for that? Well, it's gonna appear here. Okay, so K gonna be the thing that you use to describe different kind of material. All right. So if you look at the table that I have here, right? So I have different kind of material with different thermal conductivity, and you can see like different thing will have totally different K value, right? So the rule of thumb is that mostly metal is very good at conducting heat. So metal like here, so you can see there's aluminum, copper, gold, iron, something like that. So the thermal conductivity is given by this number. Okay, non-metal is usually a lot worse, like concrete. Diamond is special case because of the the structure of diamond is allows a lot of heat conduction that can happen, but that's an exception. Other than that, non-metal usually have very low heat conduction. Okay, and gas is also not so good. Okay, so you can see one interesting thing is here. Air is actually a very bad heat conductor. Right, it's almost like 10,000 times worse than aluminum. Right, so air is actually a very bad heat conductor. Right, so but you have to talk about air which is not moving, like still air. Right, if you have air which move around, then you need to consider also convection here, and that can be totally different. Okay, so in this part of the table here, that's the heat conduction. That's the heat conductivity of air, which is still air, not moving air, right? So that's something to be aware of, right? So the application of this equation is kind of very similar to the calculation of mixing that we had earlier, but the thing is that you can think about this, as the specific heat or something, because like you also have the difference in the temperature, right? So the way to use this one, you're gonna get some practice in the homework. All right. So I think this might be a good time to take a break. So I will set a timer for 10 minutes, and then after 10 minutes, then we're gonna come back and continue. So meanwhile, you can shoot me any question if you have. What is A again? That's the question. A is the area of the material here, right? So the larger the area is, the more heat transfer you're gonna have. And so essentially, it's the cross section of the area. So if we talk about like the room, then A is the total area of all the walls that you have for the room. Okay, so it's kind of like a pipe that you let water flow. If you have larger pipe, larger area, larger cross-sectional area, then water gonna flow easier. So that's kind of the same thing here. Okay, so A is this area here. Okay, all right, let's take a quick break and then we